Welcome back. It's April the 16th in not such a sunny Oxford today. Yesterday we saw the internal assessment criteria. I thought I would give you a bit of an example of what we can aim at in looking at probability as a source of internal assessment rehearsal topics. Well, we saw the criteria yesterday. The QHE in my website stands for Question, Hypothesis, Experiment. And if you think about it, in addressing personal engagement, if you're asking a question, making a hypothesis, and conducting an experiment, you've got to be engaged. You know, that's a scientific process. For sure, you're engaged in what you're doing. But really, I should go a little bit further and add a T for theory. When you've conducted the experiment, if you explain it with theory, then you're addressing the final criteria, which is use of mathematics. You're showing your understanding of the techniques of probability. So I thought we'd look at one example and follow it through that process. So the birthday problem. Now that problem asks, how many people do you need in order for the probability of at least two of them sharing the same birthday to be 50%? I'm still recording, good. Now, most people, their first answer is round about 180 people because that's half of a year, and that kind of makes sense. So here I'm conducting an experiment with 112. You can see that virtually every time I create a random sample of 112 random birthdays, at least two of them share the same birthday. So even 112 is far too big a number. So then, if this was an internal assessment, you'd reflect and say, well, it seems strange, but 112 seems far too big. If I try 32, there's our sample of 32, and they're all different birthdays. And there's one where there's birthdays shared, and there's one where they're all different. So with 32, sometimes the birthdays are all different. And I can do this 20 times. The experimental probability there was 0.65. So 65% of the time, at least two people shared the same birthday. And I collected some data here. I can copy that and put it in my calculator to make a box and whisker. I'll show you how I did this. I just pasted it here. I gave it a title, probability. I added data and statistics page. Here I put the name of the variable, and here I changed the plot type to box plot. And this is a lovely representation of the data. Remember, criterion B is about mathematical presentation. As a scientist, you can say, look, the minimum is 0.6, the median is 0.5. That's a lot more than 50%. So 32 is too big a number. And you can carry on in this way and try to collect more data, be reflective and be involved in the process. And then we come to inquiring and investigating and trying to apply some theory. So when it's a big problem, it makes sense to start with something small. This is a good way to be involved as well. In life in general, if you have a big problem, try to break it down to smaller, similar problems. So if I pick two random birthdays, what's the probability they differ? Well, why am I doing this? Because in probability, if the question is of the type, what's the probability at least two people share the same birthday? A clever way to answer that is to look at the complementary event of the birthdays all being different. Think about it. The probability that at least two people share a birthday is 1 minus the probability the birthdays are all different. Well, my birthday was April the 6th. Now I'm 50, okay? If I choose one of you at random, the probability your birthday is not April the 6th is this. 364 over 365, because there's 364 other birthdays to choose from. Okay, 3 random birthdays. Well, this time, the first birthday has to be something that is not April the 6th. And the other one has to be not April the 6th and not your birthday. Okay, so there's 363 choices there. And we have to multiply them because they're independent events. 4 birthdays. By now, you may be able to see a pattern. 5 birthdays. Okay. I'm speeding up because Tanisha is coming in a moment to borrow my room. And then a lovely thing about maths is looking for patterns. That's a way of being engaged and inquiring. So here we have all these fractions. They kind of make a nice convenient pattern if we start with this one. Think about it. The denominator is nice and easy to make into a convenient expression. It's 365 to the power 5. The top, with a bit of revision of factorials, we can simplify that as well. And if we take that further, because we want to enter this into the calculator in a moment, we can remember from the first term, permutations, this expression here and this expression here is the formula for permutations. Now we've got a nice convenient formula for the probability that n birthdays differ. Now here's a bit of revision of using your calculator. If I add a page, data and statistics, come on. No, lists and spreadsheet, that was it. Okay, if I go here and click data generate sequence, I can enter 1 minus NPR 365, comma n divided by 365 to the power n. I think that's what I said. Yeah. Okay. Gives me the sequence. I want to know the first number that gives me 50% is 23. Okay. 23. That seems incredible. Go back here. If I change this to 23, oops, come on. 23. If I do this experiment 20 times, I have to go in a minute, but you will find the data backs up that theory that you need 23 people so that the probability of at least two of them sharing the same birthday is 50%. Okay. And you don't have to just rely on a spreadsheet. If you wanted to, you could be a sport statistics nerd, look at some football fixtures. I was at this one last Saturday. The sleeping giants of Scottish football, Dunfermline Athletic, victorious for once. That's my team. If you go to any list of football fixtures, there are 23 people on the pitch. There's two teams of 11 and there's a referee. Okay, if you knew their birthdays, maybe you can find that out somewhere, and collected some data, what we're saying is we expect around about 50% of a sample of football fixtures in which at least two people on the pitch will share a birthday. Okay, so everything we've spoken about there, being engaged, running an experiment, reflecting on the data, trying to apply some theory, and then communicating it in a document that everyone can follow, that's the kind of challenge you have in internal assessment. Okay. And we're done.